little rainy Friday afternoon. My name is Stu Niebert. I am the gallery manager here at the Tucson Fine Mineral Gallery. I don't want to keep anyone waiting, so I'd love to introduce Dr. Gene Meieran and have his presentation on amethysts and calcites of Uruguay and Brazil. So, Gene, take it over.
Thank you. Are there any questions? It's hard to figure out where to start on a talk like this because it's not my normal thing to talk about such kinds of specimens. My hobby, my work has always been on single crystals, defects in crystals, crystallography, and all that sort of thing, or on some more general topics, but this one got me started a number of years ago, and it got started at next door at Danny Trinchill's place when Wayne Thompson came over and said, "Gene, you got to see this." And I went over and saw Danny in his backyard, and he had this big slab of amethyst calcite with big pieces of calcite coming out of it. And I was so intrigued. I bought the piece of it. It had to go to Germany to be trimmed out because it was about 2 meters long in the beginning. And I got enamored of the pieces, so I decided I'd get a second one. And then, like rabbits, became 4, 8, 16, 32. No, it became a substantially large number of substantially large pieces. And I just got interested in how they formed, and from a scientific perspective, it always annoyed me that you could find things where there was calcite on top of quartz and top of calcite on top of quartz, because I would say that calcite should dissolve easily. Well, how could you get quartz depositing on the top of calcite? Or how could you get calcite forming different varieties on the same specimen? It was just scientifically puzzling to me. And it remains puzzling to me, but now I'm going to go talk about the whole thing that goes back way back in time, and it'll be partially scientific talk, partially fun talk, partially just information about these interesting formations. So the agenda is going to be why. Why am I talking about this in the first place? I started giving you an idea about that. Where do they come from? How do they get there? Who's mining them? How do they mine them? And then because of the strange nature of these things, a little bit about the science of the crystal properties, and then some of the oddities of quartz and calcite, just because they are peculiar for two minerals that are extremely common. To find the diversity amongst the crystals of quartz and of calcite is rather, to me, is rather intriguing. So, how do we find the darn things? They're not hard to miss. I mean, they get to be fairly gigantic, as you can see. And can anyone guess what that looks like? Yeah, that's what attracted me about the two of them. These two. This is a friend, Sergio, down in Artigas in Uruguay. And standing between these massive geodes, and you just wonder, how does something like that form? And the thing that got me interested after the one that I got from Danny Trinchillo was this thing that was shown at the Munich show a number of years ago, and it was actually here at the Tucson show one time, and it's called the Taruga, not the Taruga, it's called the Catalana. And after it was worked on, it turned into that. And it's just, again, it's a sense of wonder when you look at something like this and say, how did this form? How did this get here? And more or less, how did they get it out of wherever it was formed and get it to Tucson or Munich or wherever they could bring them? And then there's other ones, beautiful ones with the calcite formations on them, and a bunch of them that are surrounding in this gallery that was put together by Brian with the help of Mike Hollenbeck. I had a guy that worked with at Intel named Hollander, and I always, never mind, it's beside the point. Annie and Bruce have put this whole thing together, and I'm quite pleased with the way that this whole set of displays came out. And you can see they come in various sizes with various sizes of calcites and amethyst crystals. And some of them are calcite coated with amethyst and so forth. So how did all of this come about? How did such striking features ever form? And we go back in time to roughly 200 million years ago, when the Earth was not looking quite like it looks now, with all the continents sort of crunched together. And you then had an interesting phenomenon, which has led to the study of plate tectonics. And if this works, let's see, set to point it here. Do that. There we go. Nope. Go back. No, go back and try again. How do I get it, Brian? It worked before. Brian, any information?
Oh, I just did what you did.
Okay. By the way, thanks to Brian who put it together. It's, he's the son of a very famous collector, Ed Swoboda, and has been a tremendous help. But this is looking 20 million years ago, or 200 million years ago to today, to figure out how we got here. And you can see this continent called Jai or something like that. And that Earth was still pretty hot. I mean, it had cooled down over the past 4 billion years, but it was still pretty hot. And the pieces were being formed together, and they started to separate and break apart. You can see the formation of the continents gradually taking form. It's quite interesting that you can study now, by looking at the rocks that are available now, you can piece back this history and show where things came from and how they arose and all that. Then all of a sudden we come to the ones that are most interesting to us, is the formation and separation between South America and Africa. But you see, the main thing is that at one time, I've never used this before. At one time, both South America and Africa were joined very closely, and this has an implication on the amethyst formation, which I'll show you in a moment. Okay, you can see how the places in South America where this amethyst and the calcite formed. I'm going to go back one slide. You can see here, if I can get back this slide, it shows the amethyst from Brazil on the left, and the amethyst from East Africa, from West Africa, from Namibia and that area. It's the same kind of a volcanic activity because the two parts were joined at one time. However, the crystal form is substantially different, and we'll talk more about that later on. But then you can see the areas in South America where they come from, the little rectangle is the one that's represented here. It's the southern part of Brazil and the northern part of Uruguay. And all this happened at about 200 million years ago when these things happened and the material started. Now, when I was a kid, I used to think when I started being interested in crystals that, it took a long time for these to form, gypsum or salt or quartz or what have you. Then, of course, they found in mines, they would find gypsum crystals that grew in a few days. And then they started doing the work with the quartz, and they found that the quartz took only a few days. And it turns out that the time to grow some of these large crystals is surprisingly small compared to what you might have thought at one time. So they started maybe 150 million years ago, and then they kept on going. But the crystals themselves formed in a relatively short period of time. And of course, they occurred because of this happening all over Africa as well as South America. You get the volcanic eruptions, a lot of lava coming out, which is a basalt, rich in silica and so forth. And that would form these massive lava beds, thousands of square kilometers of lava that just flowed all over the place. And as it cools, there's several things that are happening. The elements that form the basalt are separating out. Gases are forming within the material into big bubbles of gas. Crystallization is taking place slowly in some kinds of areas. And you get this funny kind of chemical pressure, temperature relationship that leads to the formation that we're going to talk about. Now, as the basalt gets cools down, it emits a lot of gas, carbon dioxide and hydrogen sulfide and various other kinds of gases, which form into these bubbles, which is the equivalent of a Swiss cheese. So these things are quite porous. They're solid rock with a lot of holes, and the holes are not contiguous with each other. They're all individuals, separate holes. But then you go through this rapid process over the next 1 million or 2 million or 50 million years. And that is what's shown in the next slide, if I can get there. And so we'll go through that. You have these bubbles that have formed in this sort of solid rock, and then you have earthquakes, volcanic activity, and all kinds of stuff that cracks open these big bubbles. So you now have a hollow bubble with a bunch of cracks around it. And water, from wherever it comes from, rain or flooding or what have you, starts to seep down through this basalt, leach out a lot of the chemicals, get into these cavities, and then you have a very, very hot water solution inside the cavities, which then starts to boil away or evaporate, and it deposits all this dissolved material on the walls of this cavity. And it dissolves fairly quickly, so you get what's called cryptocrystalline or microcrystalline materials, where the crystals themselves are, submicroscopic in size. They're crystals, but they are, you couldn't really tell that they're crystals except by very refined analytical techniques. So you get this chalcedony rim around the inside of the bubble. And then larger crystals of quartz or amethyst start to nucleate. And then the way that things nucleate, when you start a little nuclei, if you have a lot of little nuclei, what happens is one of them starts to grow and it'll consume all the resources for the others. So you get larger crystals surrounded by a few smaller crystals. Unless you have all of this porous basalt with all the sharp edges, then you get a lot of small crystals that are forming. And that's what you get in these amethyst geodes. So some of the large crystals nucleate and grow rapidly, as I say, in days, weeks, months, rather than millions of years. Then rain is still coming down and gathering a lot of ingredients, dissolving materials from the basaltic rock, and depositing them inside these cavities. So you then get carbon dioxide and working with things to form calcite crystals, which grow on this amethyst. Well, then the pressure comes in and breaks apart the geode. And when it breaks apart, the temperature drops. And when the temperature and the pressure drop, more quartz grows. So all of a sudden you have quartz growing over the calcite, which explains how this thing that puzzled me when I was a kid came about. How do you get calcite growing on, how do you get amethyst growing on quartz? Because to me, quartz should have just dissolved the calcite. It shouldn't happen. Anyway, this process then repeats itself over the millennia, and you get the calcite, the chalcedony, the quartz, calcite, quartz, and so forth. Then it builds up into these truly astonishing structures. Happens again and again with thermal activity, earthquakes, breaking it open, heating it up, cooling it down, pressure up, pressure down. And you finally get to the business where things have cooled rapidly enough so that humans come around and dig these things up and try to sell them. So here's one of the bubbles that is filled up with this cryptocrystalline and starting to be fairly large crystalline quartz. And that happens throughout the place. Now, the next astonishing thing to me was these places where they're found. when I would think about it, before I ever knew anything about these locations, I would always think about, the Rocky Mountains, and you dig a tunnel into this big mountain and you find these big cavities and you pull them out. It turns out that, if you didn't know that these things were there, you would think that you're in a rolling hills and there's nothing valuable except sandstone underneath. But it's not true. So you have these enormous caverns that are dug into the sides of these hills, and they were first discovered around, I think around the 1850s or so, because a lot of the erosion had eroded the basalt away, and these little agates started falling out in the seabed and to the riverbeds, and people started collecting them. And then you follow the train back like you would for gold exploration. They found these larger things buried deep, and then they started digging these enormous tunnels. So you get the tunnels that formed, and you can see that they're pretty big. And then they started to say, well, if it's big, there must be bigger. And if there's bigger, there must be much bigger. So they started hauling it out with heavy pieces of equipment that you see here. Now you have the kind of mining that I would have expected to see in the first place, which is quite different from what I really was surprised when I saw the formation of these mines. They're very extensive. There's a lot of digging to get these out because they are, it seems like an endless supply as well as an almost endless demand for these type of materials. Walking through there, and you can see again the countryside looks like, wow, how could there be anything like a gem amethyst underneath all of this lush vegetation? This is the person that got me one of my earliest pieces of amethyst, Harvey Siegel, for Aurora Minerals. He was at an amethyst Brazil mine, and there he's driving one of the vehicles that they have to use because the tunnels are miles long now. When they come in there, the thing that, again, another astonishing feature is that you could actually pull this thing out and it's whole. You say, how did they do that? If I crack open a geode from Mexico, I break everything inside. There's a great calcite crystal inside. I will break it in half, invariably. These aren't. And the way that they do that is that they hit the edge of the geode. They can tell it's there because it starts to be a different formation. They'll drill a little hole and put in a fiber optic telescope, microscope, or viewing system, and see what's inside there, so they know where to break the thing without damaging these phenomenal structures. So that's why you can get these structures out in these architectural forms without significant damage. Are there a lot of them? Yeah. But sort of like, to me, again, and one of those things, I'm fascinated by all this stuff, but these particularly fascinating features, like you go to the Arkansas and look at the quartz, you say, well, there's a quartz mine. But no, the state is quartz mine. And the same thing is true of these large areas in Uruguay and in Brazil. They're just enormous number of these geodes. So there's luckily there's an insatiable demand, and there's an unending supply of these materials. And here's Harvey Siegel sitting among, I don't know, this is a day or a month's worth of digging for this kind of stuff. Eventually, the mines do get depleted. Somebody has dug up all the amethyst or most of it, so they turn it into a restaurant. So you go and have dinner or whatever inside these mines. So they have use even after the material is extracted. Now, there's a couple of phenomenal things that happen with the crystals of these things, aside from the fact that they architecturally are wonderful. First thing is a thing called a skunk. And it's called a skunk because of the stripes that remind people of the stripe on the back of a skunk. So these are amethyst skunks that were once thought extremely rare. I don't know, they're not extremely rare, but they're unusual. They're pretty uncommon. And therefore, the skunk amethysts command a lot of price. This is one that was in the cover of Rocks and Minerals a number of years ago, because some articles were starting to be written about that. And I wanted to spend a little bit of time talking about these oddities. And it comes from the formation of calcite and the physical structure of calcite. Now, everyone in this room, I am sure, has seen a rhombohedral cleavage of calcite. Nice little Iceland spar that you turn around and you look through it, and you get double polarization and all kinds of neat stuff. And you think that that rhombohedron, which is seen here on the left, you think that that rhombohedron is the crystal structure. It is not. The crystal structure is shown in this diagram on the right. That is the actual crystal structure that, by definition, repeats itself through space to give you a crystal lattice. And it's actually rhombohedral, but in a different kind of a configuration than you would think of by looking at one of these rhombs that you cleave out, which is different from halite. If you take a crystal of halite, a big crystal of halite, and smash it, it cleaves into little cubes. So each little cube is almost the same as a big cube. It's not the case in the calcite. It doesn't cleave on the faces that form the crystal faces. It cleaves on the rhombohedral cleavage faces. So they really are two different things which have strange ramifications with the growth of calcite. Now, calcite is not a particularly difficult structure. It's got a calcium, it's got a carbon and 3 oxygen, CaCO3. And this is what it looks like if you were able to, shrink yourself down small enough to be able to see the individual atoms. And there's a particular property when I look at it that I see, but it is very difficult to see and difficult to represent without going to something simpler. So I'm now going to go away from calcite to use an example of what I'm talking about, which is why I believe these skunk calcite crystals occur. And that is to go to a cubic crystal. And so you see basically most of the corners of the cube are there, and then there's some atoms in the center of the faces of the cube. This is what's called a face-centered cubic atom. That's what I want to use, a face-centered cubic crystal. That's what I want to use as an example. Now, face-centered cubic is exactly what it sounds like. You have a cube with atoms on each of the corners and an atom at the center of the face. And not only an atom, it could be a cluster of atoms, like in calcium fluoride. Fluoride has got a calcium at the corners, but it has double fluoride, so they are situated around the calcium atoms. But this is just an easy representation, and you can see one interesting thing about it. There's the cubic form, but in fact, when you go down to the microscopic levels, these cubic crystals are really rhombohedral. This is something that most people that are even the professional dealers and geologists don't really understand, because this is getting down to the physics level of looking at how the detail of the crystals put together. And you can see how it comes together there, where the rhombohedron is inside that cube. The difference is that the cube has the 8 corner atoms, each shared by 8 adjacent cubes. So there's 1/8 of an atom for times 8, and each of the face-centered atoms is shared by 2 cubes. So there are 3 of those. So you get 4 atoms per this kind of a cell. That's 4 atoms or 4 molecules or 4 repeating units. The real repeating unit is the one where you have only one thing atom, and that is called a primitive cell. So we have the primitive cell, and we have the unit cell. So why don't we just use the primitive cell and all of the things? Why do we call salt cubic? Why do we call it rhombohedral? And it's because of the mathematics. If you can form a cube out of the things, let me tell you, working with cubic coordinate systems is a lot easier than working with rhombohedral systems, where you have to start working with angles and cosines and sines. With the cubic crystal, it's much easier. So it's better to use the cubic or isometric system to describe the cubic crystals. But there's an important phenomenon that I found out when I was doing my studies for my doctor's degree, and I was looking at a material called gallium arsenide. which is also face-centered and cubic. It's like sphalerite or halite and so forth and so on. And it consists of a sphalerite cube penetrated by in the case of sphalerite, a zinc cube penetrated by a sulfur cube. So you have zinc sulfide, and that is the thing. But the thing to notice is really, I may have to screw everything up by using this. Brian, I hope this works. Okay, so much for technology. You notice the green, never mind, you are not needed for this one.
I'm going to unlock this door so that I can do it shortly.
You can see the green plate of atoms. That's on what's called the 111 crystal plate. That's the normal cleavage plate of sphalerite when you cleave it. And then there's the zinc, sulfur, zinc, sulfur, zinc, sulfur. And you go through there. But if you break it on the cleavage plates, you find out that the green atoms are on one side and the orange atoms are on the other. So the first surface on top has got one set of atoms facing out. The bottom set has the other atom facing out. And therefore they have different chemical properties, even though the crystal is simple cubic. Not simple cubic, but face-centered cubic. So all of a sudden you have a thing which I found out when I was trying to make electron microscope samples, that you couldn't etch them on both sides and get the same result. You etch it on one side, it would get polished, and the other side it would become pitted. Turn it over and polish the other side, you get it polished, the first side would get pitted. So there was a difference in the way that the surfaces react because of the nature of the chemical bonding of these different elements on the surface. So what happens during a skunk, in my opinion, these are skunks to show you how they form, is that they form on the various rhombohedral surfaces, the 120 degree angle surfaces, which because of calcite's ability to be dissolved, those surfaces get shrunk down as the crystal gets bigger and these areas get smaller and you get the skunk. So the etching of the calcite is an accepted reason for getting these skunks with these very narrow lines, but I believe that the reason why they have the different surfaces is because of the nature of the chemical, the elemental facing out at the surface itself, which either attracts or repels or allows or doesn't allow precipitation. So it's a pretty unusual thing. There are other materials that show this skunk kind of hair, and I've looked at them, most of them, and they all have this kind of difference between the surface, one surface, and the opposite surface on the crystal. So you have this surface that has one set of properties, the other side that has slightly different properties. Which led me to the whole idea of quartz when, I was just thinking about this stuff. When you look at quartz from different areas, there's a Pakistani quartz, which is the typical six-sided quartz crystal with a pyramidal top. Herkimer diamonds, which are six-sided crystals with pyramidal top. Swiss crystals, which are hexagonal crystals with a pyramidal top. Afghanistan, you get some things different, which are called the Fed crystals, which grow along these white lines that are in the center. Those are a defect area. The crystals grow out. And in Brazil, you get every kind of crystal you could possibly imagine. And then in Arkansas, you get the normal hexagonal crystals with the pyramid faces. You don't get that in the amethyst from Brazil. What you get are the standard thing that you can see on the left of this picture, the standard amethyst shape. And you get big stalactites. Stalagmites, sorry. Stalactite is tight to the ceiling, a stalagmite might reach the ceiling, is how you remember it, which can be sliced and you can see the growth pattern of these particular objects. So for whatever reason, the quartz in Artigas and Uruguay and Brazil is a different quartz crystallographically from that of Switzerland or from New York or from Arkansas or from almost anywhere in the world. And so what you find in these caves are the kinds of things that are found in these amethyst geodes is a fundamentally different kind of a formation than you would expect from normal quartz. Similarly, there's other kinds of things you see in quartz that you rarely see in these quartz pieces from Uruguay or Brazil. Twin quartz. You can see, even though sometimes they look different, you can see from the red and yellow and blue lines that these are the twinning planes that when the quartz grows, it just starts off small and then it grows in these directions and forms these really wonderful quartz twins. I don't know of any quartz twins like this that grow in the amethyst geodes. Another funny phenomena that I was really interested in at one time was the quartz gwindles, where you have quartz that twists as it grows. These were really uncommon except in Switzerland for a long time. Now they're fairly prevalent in Pakistan. There's a couple of other places you find it, but the quartz gwindle, you do not find gwindles in the Brazilian beds. Scepters, same thing. Those are just secondary growth. You grow a crystal, something happens, it stops growing, new solution comes in, it grows what's called epitaxially on the first crystal, and you get another one, maybe with amethyst on the top or amethyst on the bottom, or whatever it is. And these things grow up, and you have gwindles, twins, scepters, which are rarely seen in the Brazilian or the Uruguayan amethyst. So I put my own table together that sort of illustrates this. And I put down the different areas of commonality and the different areas of uncommonality between the... Now remember, almost all the quartz is formed by the same mechanism, by hot solutions of water that deposit silica somewhere. That's generally the formation of quartz. Water dissolves the silica from surrounding rock, precipitates it out at some point when the water cools down or the pressure drops. You get these quartz crystals, but even though the beginning is the same, the response is quite different depending on the location of where it comes from. So twins are occasional in Arkansas. They're very common in pegmatites. Don't know of any in Uruguayan amethyst. They're sort of rare in the alpine and so forth. So you can see from this table different kinds of formation, but of course you get the common formation of stalagmites in the Brazilian and Uruguayan quartz, but you don't see that very often in the other kinds of quartz. So it's kind of interesting to look at this and try and see what the commonalities and the differences are, even though the elemental crystal shape, the formation of the crystal, the water dissolving and reprecipitating out the quartz, we wonder about that. So much for the science, but then there's just the aesthetics. And you don't have to look at these pictures because most of these specimens are here in the gallery that Ian put together. And again, to me, it's astonishing that this could happen. That one on the right is a calcite crystal. They grew all the way up to the thing, and then quartz amethyst came out on top of it. By the way, one of the other things I did not mention in this table is that the color. The amethyst color comes from a different kind of iron, very small, minute traces of iron in the crystal. So iron, if you think about it from a mineralogical point of view, you have a mineral FeO, iron oxide, and you have a mineral Fe2O3, two different valence states of iron. Neither of them are magnetic, but you put them together, FeO plus Fe2O3 forms Fe3O4, which is magnetite, which is heavily magnetic. In this particular case, the Fe2 doesn't react with the light coming in, but the Fe3 valence does, and that is what, plus radiation from the igneous rocks that have uranium and thorium and all kinds of crazy radioactive material in them. That radiation hits the iron 3 and changes the color. That's what gives you the color in amethyst from these particular areas, and I guess from almost all areas, which is rarely seen in other places, certainly not seen in the cases where like in Arkansas, which is, a sedimentary type of deposit. So again, you see all these really strange shapes. This comes because calcite is just prolific. Quartz comes in generally six-sided things with pointed tips. That's almost all of it. Calcite comes in 10 zillion different shapes and forms, which is why these things look so attractive. I mean, how can you not like something like that? These are two of my favorite. This one on the left was one that, the second one that I got really, I was shown to it by some people from Brazil. And I looked at it and said, no, these are people from Uruguay. And they showed it to me and I said, I got to have it, mainly because I was going to talk to Barry Yampel about it, see if he liked his name engraved in rock. The one on the right is a recent thing, and I've never seen anything like it. It's a big plate of calcite with spikes coming out of it. It looks like an alien creature.
Those are down at the museum if they want to see them.
Yeah, I was there. A couple of these things that are at the these two are at the Arizona Museum on display if you wanted to see them. And from my point of view, yes, they are worth seeing. This is one that we have in our kitchen, and I just call it the architectural genius, which brings me to why are people interested in this? Because they are unusual, like the one on the right, with these long crystals that grew up. This one on the left was a slice of a big geode, but what had happened is that you had the liquid, and it formed a skin, and when the liquid drained out or evaporated, it left the skin, which was quartz crystals. So it's actually a transparent, translucent layer of quartz crystals on making what would have been the surface of a liquid that was in there. And sometimes the calcite dissolves out and you get these framework of calcite that was there and them. And then one of my favorite, which is the one in the center of the hall there, is the one where you get the wonderful spikes of calcite coated by amethyst. And then a big one, it's not here, but it's about yay high, and it's got this big spear of the torch. And this is one I got from Harvey Siegel after I sing, and I had to get it. So what does that remind you of? I can't help doing that, I'm sorry. So why do we do quartz? This is a tribute to Jim Zegras, who's doing the quartz mining in Arkansas, where you find these phenomenal large quartz. Quartz, why? Because it's really neat material. It's just wonderful, surprising material. Okay, but why amethyst? Because where else can you find something where you could climb into the specimen and enjoy it from the inside instead of looking at it from the outside? And I would point out that I am not the only one that appreciates these crystals. The orcs liked it as well from Lord of the Rings. That one is here. We moved it from the orc land, from wherever. What's the name of the city? Anyone know what one of the cities is? Huh? Mordor, good. This was moved from Mordor, is now here at the gallery. So, I'm not the only one person that treasures these things. I really do like them. My conclusion is, Mother Nature has been stupendously generous in creating these things for us.
Gene, you want to tell me why some of them keep the iron in them?
Pardon?
You want to tell us why some of them keep the red iron color? Like.
Oh, no, I don't. The problem is that the chemistry of these things is rather complicated. There's, only in a few elements, but there's a carbon, silicon, oxygen. Those are the main things. So calcium carbonate, silicon dioxide. But there is iron, because iron is pervasive almost everywhere, and it's leached out. And the problem with iron is that, as I say, it could take two different valence states, either a +2 ion or a +3 ion. And when it gets in there, it can form limonite, magnetite, hematite, inclusions, stains, rust color, and all that. So it's hard to explain without going into detail on any individual specimen. But the iron is just sort of a substitute for the silicon atom in the crystals, and therefore it can be either interstitial, meaning in between, or replacement. And then it's very easily affected by radiation, which changes the valence state, which changes the color.
You mentioned that some of the crystals are formed, you said not over light years, like you said, hours and days and weeks.
Yeah, yeah.
What about in the middle, like years or tens of years or hundreds of years?
Well, of course, all these crystals depend on a few factors. The temperature, the pressure, the composition are the three main ones. But you're really not depending on those. What you are depending on is the rate of change of those things. How does the temperature change over distance? The rate of change of temperature over distance. How does the temperature change over time? The rate of change over time. How does the pressure change if you take something with a high pressure bubble and you puncture it? Well, a balloon, it deflates very rapidly. But if you did it with a big life raft, it would take a while for the thing to deflate. So you have all these combinations, and the rate of change of these is what determines how fast the crystals precipitate. Do it rapidly, you can get very, very rapid crystal growth. So I remember in a chemistry class, you take what was called, used in film, then for developing films, for fixing film, was sodium thiosulfate. And you can take a spoonful of these crystals and heat it up with a little match or a torch, and it becomes liquid. And then you could slowly cool it below the cooling temperature, the freezing temperature. It would stay a liquid. And then you drop a tiny pinprick of anything in a piece of dust, and it crystallizes instantly. So you can get instant crystallization like that to days, like for sugar and stuff, days that takes for quartz crystals, weeks that it takes for semiconductor crystals, these large ones, to grow. Months. Diamonds are different, entirely different story. They form only under tremendously high temperatures and high pressures. So the answer is that there's too many factors in too many different locations, even for the same material. Yes?
Why does the calcite always exhibit the same sort of range of colors on these specimens?
Again, just the chemical composition is the iron. It's almost all of this is due to iron ions somewhere deposited in there. Occasionally you get an excessive amount and you get it to be orange instead of yellow. And other times you get it with a deficiency and it turns sort of whitish compared to that. And again, you can get the quartz to be normal amethyst color. If it gets heated up by something, it turns yellow. So you get the citrine geodes. And if you do it the other way, you can get the quartz to become white. So you can have white geodes, amethyst geodes, and citrine geodes. It's all this pressure, temperature, composition, and the rate of change of these things that makes the difference.
The mine that turned into a restaurant.
Pardon?
The mine that turned into a restaurant, is that in Brazil?
It's in northern Uruguay, in Artigas, outside of Artigas. There's a difference in the quality of I won't say the quality. There's a difference in the properties of the amethyst between Brazil and Uruguay. Uruguay, you get more of these kind of formations and a darker amethyst. Brazil, you get larger crystals, sometimes a little bit paler. But there's about, 1,000 kilometers between the top of the amethyst deposits in Brazil and the bottom of the amethyst deposits in Uruguay.
Really good.